Hey, calculus, what's going on? Today we're going to start talking about the types of functions, how to identify them, and understand exactly kind of the inner workings of a function in a very simplistic way here, okay? So make sure you have a piece of paper and something to write with, and we're going to go ahead and get started with our warm-up right here, which is to create a value for the table, create a table of values for the function f of x equals 2 times 1/2 raised to the x power, okay, where x is any real number. So how we do that, I'm sure, just as a quick review here, what we're going to do is we're going to, right here, put a little table here. We're going to have x and then f of x, just like we would have x and y, but we're going to use f of x here because this is a function. This is function notation. And for this problem here, because our variable, our input variable is an exponent, this is what we would call an exponential function. So the couple values that we want to test out are -3, -2, -1, 0, 1, 2, and 3, like that. Okay? So I'm going to give you guys a couple seconds to go ahead and try that out, and you're going to plug in these values that I have on the left side here. You're going to plug them into the function and let me know what you get back from that. All right, so now once you have that done here, what you should see is this is what you should have for a table of values. You should have 16 for -3, you should have 8, and then 4, and then 2, 1, 1/2, and then 1/4. And you can go on to 4 and get 1/8, but that's basically what you should have as a table there for this function when you raise 1/2 x to, or 1/2 to the x power and then multiply it by 2. That's what you should get. So what I'm going to do is I'm going to take this table here that I have and I'm going to, let's see, can I copy this? Yes, I can. Okay. And I'm going to post it over here to the next page, which, let's see here. Can I do that? Can I paste here? Let's see. Edit. Can I paste? No? Well, darn. Okay, that's all right. I'm going to go ahead and redo the table over here. So we go to Sketch It. That's x. Here's f of x. Okay, so remember, -3, -2, -1, 0, 1, 2, and 3. And then you're going to have 16, 8, 4, 2, 1, 1/2, and 1/4. Okay, so when we go to plot this curve, this exponential function here, we're going to treat this as if it's an ordered pair. So -3, -16, which is really close to 0, but not quite 0. Oops, I'm sorry, -3, +16, which, let's say that this is all worth 2 here. So 2, 4, 6, 8, 10, 12, 14, 16. So -3, 16 would be about right there. -2, 8. So that's going to be right here. -1, 4. And then 0, 0, 2 is right there. 1, 1 is going to be right here. And then 1, 2, or 2, 1/2, and then 3, 1/4 is right here. So our exponential curve is going to look like this. It'll get real close to 0, but it won't ever exactly get there. Okay? Now, let me ask you this. Let's say instead of multiplying by +2, let's say we have -2 here. Okay, so -2 times all that. Well, we can take what we have from that function. Let me see if I can group this together again. Let me see if I can copy and paste this. I'm going to try this one more time. Let's see here. Oh, cool. Okay. Can I put that over on this guy? Yes, I can. Okay, I learned a new trick today. All right, so now if we're sketching this right here, and now we have our exponent change, or our coefficient change to a negative number. Oops. All that's really going to do is, now we're taking 1/2 to the x and multiplying it by -2. So now our coefficient changes from positive to negative, so now we're going to have the points -3, -16, -2, -8, -1, -4, 0, -2, 1, -1, 2, -1/2, and 3, -1/4. So I'm going to put that in blue here. So -3, -16, so left 3 and then down 16 if we scale it the way that I had originally, which should be right about there. So -3, -16 is right there. -2, -4 is right there, or -8, I'm sorry. -1, -4 is right here. And then 0, -2, 1, -1, 2, -1/2, and then 3, -1/4. And then once again, because it's exponential, we want to go ahead and connect all of these to a curve. You can get real close to 0, but not quite get there. Okay? So that's f of x equals -2 times 1/2 x, or to the x power here. Okay? So the next part of our lesson is going to be talking about the degree of a function. Okay, so we dealt with an exponential function. Now we're going to talk about degrees of a function. And all a degree really is that if you put a function or any polynomial into descending order, where the highest exponent goes first and everything else after that comes after it, that would be what we have circled right here for -x⁴ plus x² plus x. So the degree of this function right here would be 4, okay? And if you were to put in the calculator, there is a function on our TI-84s that if you put DEG parentheses, you put a whole polynomial here, what the TI-84 will do is it will search for the highest exponent, which in this case we know just by looking at this to be 4, and it will give us 4 as a response here. Okay. The next thing we want to talk about with functions is whether or not a function is odd, even, or neither. Okay, so there's a couple things we want to take a look at. First of all, the easiest way to tell if something is odd, even, or neither is we look at the exponent. So for instance, looking at the first function here, we have f of x equals x² plus 6. So we look at the exponent right here. That's an even number, therefore this function here, this first function, is going to be even indeed. Okay? Looking at the next function, we have f of x equals x³ minus 8x. We look at the highest exponent, that's a 3. That means that this is going to be an odd function for this part right here. And then looking at the next one, x⁴, f of x equals x⁴ plus 3x². Highest exponent is 4, therefore this is going to be an even function. Okay? So one way we can tell just by looking at odd, even, or neither is if we know what the function is, we look at the highest exponent, and if it's even, it's an even function. If it's an odd number for the highest exponent, it's an odd function. And, interesting to note, if we have neither an even nor an odd number, so for instance, if we have something that looks like this, f of x equals x to the 2.5 power, something like this, so 2.5 power. It is a function, we can put in a number for x, but that 2.5 is neither odd nor even. So therefore, this would be considered neither. Okay. Another way we could tell if a function's odd, even, or neither is looking at its end behavior. I'm going to use pink right here, or I guess that's magenta, so to say. But for right now, let's take a look at the end behavior. That means looking all the way to the right, all the way to the left. If the end behavior for a graph is same, both up or down like this, that makes it an even function. Okay. But if the end behavior, for instance, for the green graph here, if going towards negative infinity is down, but the going towards positive infinity is up, that means that this is going to be an odd function. Okay? Now, what we have here is, on the end graph here, is a circle. Okay? And because we can't tell what the end behavior is, this is going to be considered neither. Okay? And besides, it would be something probably along the lines of x² plus y² equals 8 or something like that, where we have both x and y on the same side. It's a function of both x and y. From that, we cannot determine if the function is odd or even. Therefore, it has to be determined as neither. Okay? Another quick rule here is that algebraically, if we have a function and we put in a negative number, or if we put in, like for instance right here, it says negative x, and we get the same value out as what positive x would be, that's one way we can also tell if it's even. Okay. Another way would be too is we plug in a negative value for that and we get the opposite value of the function here. That's a way we can tell that it is odd. But if we end up with something like this where we plug in a negative number at the end and it doesn't equal that, it would be considered neither. Personally, I don't like using that just because it can get confusing, so I prefer using the first two ways that I showed you, either by looking at the function itself or its graph, and that is the easiest way you can tell if it's odd, even, or neither. Okay, so moving on here, I'll give you guys a little bit of time to write this. You can feel free to pause this if you want to. If a polynomial has an even degree, it is even. Okay, so we have a degree of 2, 4, 6, 8, 10, a million. As long as it's an even number, it has to be an even degree. Okay? Therefore, if a polynomial has an odd degree, it is an odd function. So odd. Okay, so once again, let me give you guys a little bit of an illustration here. Therefore, it would look something like this. For an even function, it would have kind of a U shape like this, or it would have an N shape like that. If it's an odd function, that means that it could have one end going up like that, another end going up like that. It could also have a little bit of curve, but as long as the end behaviors are opposite, that means that it is an odd function. Okay? If a function is not a polynomial, remember, a polynomial is any type of function where it's basically, so something like x to the n plus x to the n minus 1 plus something like this. It keeps going down, and then we finally end up at x plus some constant value. Okay, as long as it has something like that, it's a polynomial. So if it doesn't follow this, where n is an integer and everything like that, then it cannot be, it is neither odd nor even. Okay, moving on down here. We talked a little bit about this in the last lesson, increasing or decreasing intervals. Okay, so for this activity, or this slide right here, notice how when we're talking about increasing functions, it's going to be the part where, okay, so we have a point right here and another point right here. Notice how from the end of the graph to the top of this little hill right here, this is what we would consider an increasing function. But between that and the next point where it kind of flattens out, it is also decreasing because it is going down from one point to the next. And then after this little low point here, it does increase again. Okay, this is a very general graph. I want to show you a more specific graph here. Okay, so looking at this function right here, this graph right here kind of shows us the points of where it kind of flattens out a little bit. We would consider after this point right here, this first green point here, everything from the left up to that green point would be considered an increasing function. All right, everything between that and the second green point, notice how the graph goes down. If you follow it kind of like a slope like this, that is a decreasing portion of our function. And then if you follow that all the way up to our third green point, it is also increasing here. Now what happens to the right of this third point is, notice how it's flat from there onward. That means that it is neither increasing nor decreasing. It is constant. Okay, so I'm going to illustrate this for you guys one more time. Okay, so from here it is increasing here from negative infinity to that point there. Afterwards, from that second point, the first point, it decreases. And then it increases again past that second green point. And then after that, this flat region right here, this plateau, is considered constant. So neither increasing nor decreasing. Okay? And to give you an idea of what it looks like if we were to put it into function notation here. All right? So now, once again, we want to think of it going from left to right. So starting at this point right here, these are what we call points of inflection, guys. Okay, so where it changes from positive or increasing to decreasing. These are points of inflection. Okay, so we have our 3 points right here. So we're going to say, let's take a look at this in terms of function notation. So increasing intervals and decreasing intervals. First of all, let's go from left to right. So from this point onward till it gets to right here. So from left to right, it's going down. Therefore, we would say that the interval here is going to be from negative infinity to the x value there, which is -1. Okay. Then after that, we see that this interval here, it is increasing. So from -1 to 0, it's increasing. Now, these are intervals here. So we don't want to create another interval until we say, hey, this is part of, we want to add on to this interval. We use that using the capital letter U, okay, because we see we have a couple more intervals we need to get through. So U kind of signifies a union between our sets here, okay? So the next right here, this part right here, from left to right, it goes down, it decreases. So therefore, we mark this interval as, let's see, it starts at 0 and goes to 1. Okay, so those are decreasing intervals. And then from there, notice how it goes up from left to right. Therefore, this right here is our last increasing interval. So that's from +1 to +infinity. Okay? All right. So make sure you have this video watched. Bring your questions to class, and we will see you very soon. Have a good day, guys.